It's about time to get started, so I'll begin by welcoming all my friends and some strangers as yet to be friends. I am Mark Kiel. I'm the Chief Science Officer and founder of Genomenon, and today I'd like to talk to you about variant interpretation at scale, particularly as it informs newborn sequencing. So I was having breakfast with David Bick from Genomics England the other day, and he talked about newborn sequencing where the name of the game is variants. And the way to win that game is with evidence. And that's what I hope to outline in my slides here at a very high level, and happy to address any details that I'm at liberty to address in the questions. This is how I'm going to outline it. Very succinctly, I'm going to talk a bit about newborn screening and how it contrasts with newborn sequencing. I'm going to discuss the Genomenon technology and specific applications in this vein, and then address several specific challenges and highlight how those are being addressed by my team. So to begin, about newborn screening, to really emphasize that it's a triumph of public health policy. And there's no reason that newborn screening and newborn sequencing should be at odds. In fact, that's how many of my collaborators and I view this, is that they are to be united in the same common goal of identifying patients through the screening process. Into this environment, genome sequencing promises to broaden the number of diseases that are sequenced, identify pre-symptomatic individuals, and also facilitate homogenization of testing across these labs. But clearly, many challenges exist, and those span the gamut from the technical to the ethical. We're more on the technical side, and I'll be addressing, as I said, the specific lane that we're driving in as we pursue this common goal. As I mentioned, winning this game is predicated on evidence, and specifically in the context of newborn sequencing, that evidence is going to be used to ensure maximal sensitivity and specificity, where those are very naturally to be balanced, and that's one of the major issues that attend the implementation of newborn sequencing. Obviously, the impact of such screening programs facilitated by newborn sequencing is to be measured, and into that consideration are the costs associated and the time it's going to take to get there. But as I learned in a panel discussion with Heidi Rehm at the ICONS symposium several months ago, one of the most important challenges, and certainly the one that we're most focused on, is the challenge of interpreting these variants and their clinical meaningfulness. Additional challenges downstream of that interpretation remain for full implementation of newborn sequencing. That is to say that there's too many variants and too many patients who need to be assessed for this to happen in real time. Real-time interpretation of variants is not feasible to meet these cost and time considerations. In particular, there's too few analysts to do this job, there's too little time to do the job within those workflows, and there's too little coordination across labs. So in order to address these high-level challenges, we're proposing a completely different approach. In order to meet those scaling issues for full newborn sequencing implemented in the context of screening, what we see as the greatest need, and is echoed by many of the people that I've talked to just this week, is a database of every one of these actionable variants in the context of screening, all interpreted and serving as a lookup table for easy access and corroboration of the evidence that supports their actionability. So that's the challenge. The solution is to curate the entire genome. And that may sound like an ambitious, even untenable goal, but let me walk you through how we're doing that and emphasize that we're doing this in partnership with a great number of newborn sequencing providers, including Rady Children's and the CDC. Our role in that, as I said before, is to facilitate variant interpretation by being the evidence broker, by pre-curating the genome, as I'll speak to in a subsequent slide, and providing all of that information to the clinicians who are then going to make the call to inform the composition of that lookup table. So let's go into some more detail about what I mean when I say a fully curated human genome. This is to say, for any disease, for any gene, and any variant in any one of those genes, every reference and every database pull that's necessary to interpret the meaningfulness of those variants is all precogitated, pre-organized and pre-assessed in the context of screening, and then presented for corroboration, for adjudication, in the context of the screening paradigm, and then subsequently when diagnostic considerations are at play in the clinical context that attends that specific patient. How to get there is challenged by an issue that I'm sure many of you have faced, is there's a great proliferation of this information in published literature or in unstructured references. That's the clinical information and the functional characterization of these variants that has been afforded by revolutions in genome sequencing. So there's this great proliferation of knowledge, but it's distributed across multiple different publications in very unstructured contexts. So the solution that we need to implement to rise to that challenge is to employ computational intelligence. The computational intelligence here is different than the AI you might have heard of. I don't want to have these two be confounded with each other. There's a great deal of noise about AI in the commercial space and the public space. I want to talk very specifically about what our computational intelligence looks like and why it's different, and then how we pair that with human review to ensure that everything is as specific and accurate as can be. But in this context, the computational intelligence is to ensure that that great proliferation of information is completely cataloged so that nothing is missed, so that we have the utmost sensitivity in the data that we're presenting. And this is a schematized version of our core technology, one of them, a major one. We refer to it as genomic language processing. So that proliferation of information that I talked to on the subsequent slide is on the right or left, depending on how you're looking at this. It is what I call the chaos of that information. And on the right, and the process to get to the right, is the order. The structured way to parse that information, leveraging the computational intelligence that we've referred to as genomic language processing, to identify those diseases, the clinical phenotypes and the functional studies, the therapies that were tried or tried successfully or tried without effect, and obviously critically the genes and genetic variants in those genes that are seen in these patients, all of which can be organized into genomic associations and used to facilitate interpretation of the meaningfulness of these variants. Importantly, genomic language processing recognizes all of the different ways each of those entities can be described by authors. And most critically, the vagaries and complexities of genomic language at the variant level. RSIDs, cDNA, protein changes, HGVS fidelity or infidelity, as well as transcript issues and legacy issues that can be haunting the literature from 10, 20 years ago. So genomic language processing is a capability that we developed 10 years ago and have been perfecting ever since, with increasing attention to these details across all of the scientific publications across every gene. And where that has culminated, as many of you know, is into the Mastermind Genomic search engine, which can be queried any one of those specific nodes of information, disease, phenotype, therapy, but also very critically any gene or any variant, to retrieve that information in a highly sensitive way, and to decorate that annotation with any of those other terms to enhance the specificity of that result. So that genomic search engine comprises 9 million prioritized full-text references that have genomic content, as well as 3 million supplemental data sets, and culminates in the most sensitive database of genomic information at the variant level, and is used by a great number of labs across the world. I mentioned that to meet these needs, especially with the clinical acuity that's demanded by the circumstance, we cannot rely on computational intelligence alone. And the challenge here is to say that accurately interpreting that information requires a human, and we obviously fully endorse that. We have many humans employed by our company. The solution to that challenge is that curation by experts is vital, to ensure that you have the appropriate balance between the sensitivity and the specificity of the information that you're surfacing. And we have a unique combinatorial approach to this. We leverage the computational intelligence of GLP that I described, and have a team of experts who are trained in the process of reviewing this variant information and cultivate an expertise in these disease-specific and gene-specific idiosyncrasies. And what results then in the process of curating the entire genome is a very sensitive and specific reflection of the sum total of this data that is needed to drive accurate newborn sequencing. We hew to the accepted curation guidelines, which you're undoubtedly familiar with. That's to say the ACMG criteria published in the Richards et al. Paper and soon to be updated. Very important to say is that the process of updating this information will be very straightforward for us, though the new guidelines may be Byzantine, because we have a technical computational platform that supports all the previous curation, and making the appropriate modifications will be, as I said, very straightforward. And will perdure as we continue to curate the rest of the genome. So I alluded to the balance that needs to be struck between the sensitivity and specificity of that information. And I want to highlight that with a specific example. Some of you may be familiar with the ENPP1 gene. It's associated with a rare disease, a couple of rare diseases. One of the most devastating is generalized arterial calcification of infancy, caused by mutations in the ENPP1 gene. One of those mutations I'm displaying here, it's actually the most common variant among disease cohorts of infants and toddlers who have this disease. And importantly, the call in ClinVar on the bottom line says conflicting. And the reason for that is because there was one or two submitters who had a dissenting view on the nature of that variant, whereas 3 or 4 referred to that variant as pathogenic. So there's reasons behind the call of benign, the clinical circumstance, the disease by which that variant was being interpreted. So I'm not impugning the quality of that result, but what I'm indicating is that the very specific attention to those details is what's required to produce this variant lookup table, rather than rely on a database of information that has not been exhaustively reviewed and was certainly not reviewed in the context in which it's intended to be employed. And just to call that out, this is the variant, and there's very clear evidence from segregation studies and functional studies, which comprise much of the ACMG interpretation criteria, that demonstrate that this variant is pathogenic. But nevertheless, it's listed as conflicting in ClinVar, so if you were to apply an automated approach to incorporating a public database such as ClinVar, you'd miss out on the most prevalent variant, leading to an inability to effectuate change in the clinical management of individuals with generalized arterial calcification of infancy. So that's anecdotal, or anecdotal as I like to say. That's one example. When you amortize that across every gene or every disease that's relevant to newborn sequencing, you see patterns like this emerge. I'm a huge fan of Venn diagrams, but let me walk you through it, though it's complicated. On the right side are those clinically encountered variants that are promulgated or uploaded into ClinVar, a very important resource to capture those clinically significant variants. But the reflection that I want to showcase here is that it's not the sum total of all of the variants. On the left side of this diagram, the blue crescent is a reflection of those variants that are not in ClinVar, in this specific gene, but that are nevertheless clinically significant, where there's sufficient evidence to indicate that those variants are actionable and meaningful, whether it be functional or clinical information or both. And then importantly also in the middle, there's an overlap of those variants. So there's variants that are only in ClinVar that are encountered clinically. There are variants that are only in the literature that aren't currently in ClinVar, and there's variants that are in common. But there's situations, as I alluded to with the ENPP1 example, where there's disagreement in the interpretation of those results. Whether it be because it's a low star rating, there's one submission, there's a different clinical circumstance for that variant, etc. But there's reason to wonder about the veracity of those calls. And if you'll recall how we began this conversation, the way to win those arguments is with evidence. And that's what we're talking about, as I said, organizing and annotating and making sure that the evidence is being utilized. So in addition, there's a lot of idiosyncrasies, disease by disease or gene by gene, and I'm highlighting some of them. There are many more. These are top of mind for us. I'm just going to point out a couple here. One is the clinical significance of variants of uncertain significance. There's clinical circumstances that attend some patients that can promote a variant of uncertain significance to likely pathogenic. And that challenges the notion that you can build out a lookup table. But we're not daunted by that. In fact, as I said, we're in our goal of realizing newborn sequencing, our goal is to get that information out and maximally utilized. So when there's newborn sequencing that may be followed by confirmatory testing to assess the biochemical nature of that patient's samples, this is where the data will reflect how important clinically significant VUSs may be. And especially when we're talking about another bullet point there is staying up to date. Staying up to date with the literature as it's continuing to proliferate, and staying up to date with those guidelines as they change. All of that information, including incorporating the information that's learned in these pilot studies, will be critical to ensure that this is a reflection of the totality of the data needed to make this success. So a couple more components here. Another challenge, as I've alluded to, is ensuring this information is readily available. So I mentioned that we have Mastermind, the genomic search engine, and that we have a broad user base across 140 countries, many tens of thousands of users. So this is a platform for that dissemination. This is a reflection of our global footprint with some of the names that you'll recognize who are using Mastermind in their clinical workflows. This is where there's new information, a new concept, is rather than have Mastermind serving up the evidence and leaving it to the variant interpreter in the clinical circumstance to review that information. We have pre-curated that information and presented it to those users when they perform that search. And so there's many of these, though you could still consider them Easter eggs. If you've used Mastermind and performed a search, you may have run into some of this pre-curated information. And just as I described, all of that information pre-annotated and decorated with the disease and phenotype of relevance is presented to the end user to allow them to draw their own conclusions very quickly and very accurately. And you're just seeing a reflection there. This slide is meant to showcase that we have clinical and functional information in those interpretations, as well as the requisite database integration that's necessary to interpret these variants. So the last challenge that I want to illuminate here is to ensure the full culmination of the potential benefits of newborn screening and newborn sequencing. I feel like there's the necessity to collaborate across multiple different industries within this ecosystem or disciplines, be they academic, be they patient advocacy groups, be they industry, or be they biotech. And so partnering with pharma is something that we've begun doing in the context of these gene-by-gene curations, one of which I alluded to earlier, which is Inozyme, which I'll showcase here in a subsequent slide. But what pharma needs to ensure that they have the best likelihood of success of their program is that evidence. They're playing the same game with the same common goal. This is utilized for optimizing clinical trial design, but also de-risking trials and ensuring that the right number of patients can be assessed to inform how strategically to develop your drug program. So we have a whole suite of tools that are geared toward pharma that leverage that curation capability and address those specific issues that I spoke to. What are the causative variants in this gene? What are the patients that are likely to respond to my intervention, especially if it's a precision therapeutic? What is the number of patients that we're likely to see, which is critically important in rare and ultra-rare disease? And what is the nature of the way those patients look, tantamount to a retrospective natural history study? And so we have solutions that address all those issues and provide value to our pharma clients in those different ways. And there are some of those who are listed here, whether they're constitutional disease all the way to cancer. As I said before, we're talking about newborn sequencing, which has to do with rare disease, but we also have the data that's necessary for oncology programs as well. So I'll end here by talking a little bit more specifically to that Inozyme use case that I alluded to. I mentioned the disease. We're in partnership with Inozyme Pharmaceuticals to help promote awareness of the therapy that's currently in trials for this disease, as well as to bring awareness of the prevalence of this disease, which is much more common than previously recognized, and which in collaboration with Inozyme, we produce data to prove. With our data, we took a consideration of prevalence from 1 in 200,000 to 1 in 65,000 with the data that is maximally sensitive, so has a capture of all of these causative variants and is predicated on that evidence. So there's a high degree of confidence that there was an underappreciation of the prevalence for that rare disease. So this is, I think, my final slide. Let me end on an optimistic note because I'm an entrepreneur and I'm somewhat forced to be by nature. But the way I see this information integrating into newborn sequencing is that the more sequencing that's done, the more evidence that will be published and the more cases will be submitted to public repositories like ClinVar, the more newborn sequencing, now in pilot phase and early stages, but as we move through the years, the more newborn sequencing is performed, the more it will continually improve, and the more patients' lives will be positively impacted. So that concludes my talk. I'm happy to take questions from the audience now or at the Genomenon booth, which I believe is 1107, as well as approaching some of the Genomenon folks who are in the back who would be more than happy to scan your badge for a subsequent conversation. So that concludes my talk. Any questions, I'd be happy to entertain. So the question for those who couldn't hear is, could this information be integrated into analysis software? So the answer is yes, the short answer. The longer answer is that we have a number of integration partners with tertiary software providers, and most of them are now using the mastermind data as I described, and we're in talks about getting that curated data integrated as well. The other thing to say is that we can work with homebrew solutions who develop their own infrastructure to insert some of that curated data. And then obviously in our collaborations with these newborn sequencing providers, that data is integrated into those workflows. It's a great question.
Expert reviewers, are you using the CAP guidelines as far as credentials?
Yep. So the question pertained to our team of curators and their approach. So let me say first that they're great in number and they're also extremely well trained. Master's level and above. We have genetic counselors who are supervising this information and have decades of experience in variant interpretation. The guidelines that are being followed are the clinical standard guidelines, whether they are the ACMG, AMP, CAP, CLIA framework, or if there are ClinGen guidelines that are put forth for any of those disease-specific considerations, those too are incorporated in the interpretation. And I think most important to emphasize is that information is presented to you. So you'll see the work, you're free to disagree, but we'd like you to disagree with evidence as opposed to opinion. That's a great question. If there are no other questions, as I said, I'm happy to entertain any questions should you wish to approach me at the podium or email later. May? Yeah. Yep. The question pertained to the downstream integration and use of this data. Is in the public health setting when you're screening many, many cases, there's still the need to look at that information. So it's important, as I said, reiterate that we're in the pilot stages. That's the first thing. And then to remind that I said that this is the infancy of newborn sequencing. And at a certain point, we're going to have such a burden of information about specific variants and specific cases with some longitudinality to the patient that we'll be able to make a yes or no decision with a computational approach alone. We're not there yet, but it's still a laudable goal. And I feel like with time and with more data and more coordination, we're going to get to that situation for the majority of the variants that we're screening. Sure. Yeah.
So some point, I think a lot of some lab have
Yep. 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 Great question. So May is alluding to some intrinsic limitations to the public information, the published information. She's speaking about some other predictive models as well as some functional genomics. It's empirical data. And so we're integrating those lines of evidence. We're working with some functional genomicists to create that data to ensure that the totality of the evidence that should come to bear for each of those cases is present in this platform. So those efforts are ongoing, and as I said, are really necessary to ensure that we've laid the groundwork for a successful 5 or 10 year outlook. So thank you all for your kind attention.